Hello everybody! Welcome to Math 251. My name is Amanda. I use she, her, hers pronouns, and I am so excited to be your Math 251 instructor for this term. I know that for a lot of us, this is not the way that we planned on taking Math 251, and so I hope that you have already read through the course guide as well as the syllabus. If you've not done that already, then please pause this video and go look through the course guide and the syllabus. There's a lot of information there, so please do take the time to read through both of those. I think that it will be able to answer a lot of your questions about how this term is going to work. But basically, in terms of the lectures, I am going to be posting a lecture video pre-recorded of the sections that we are covering for the week. So I'm going to be posting them the day before we would have covered that material in class. So please watch them before your scheduled class time. And then during our scheduled class time, I'm basically going to be holding office hours or discussion hours via Zoom. So that will be online during our regular class times. So I hope to see many of you there. And yeah, so please don't hesitate to reach out to me via email anytime you have a question. Again, I know that this is not an ideal way to learn Math 251, so please do not hesitate to reach out to me. I really want to help you succeed this term. I know that a lot is going on in all of our lives, especially regarding these different circumstances. So I want to help you succeed. I care about you all as students, so please do not hesitate to reach out via email or Canvas. Okay, so like I said, I'm going to be posting these pre-recorded lecture videos, and let's go ahead and get started. I really like to highlight mathematicians who are women and people of color in this class, as well as I like to talk about math history facts, because not many of us know about math history, and I think it is really fun. So every day we have a mathematician of the day, and today's mathematician of the day is Sophia Kovalevskaya. She was a 19th century Russian mathematician who was the first woman to obtain a PhD in math, and she made huge contributions to several fields of mathematics. And today's math history fact of the day is the Pythagorean mathematician Hippasus. He discovered irrational numbers like pi. He was murdered by the Pythagoreans, because back then irrational numbers were considered blasphemy, so he was murdered. Aren't you glad you live now? All right, so the first concept we are going to talk about is the concept of a limit. And we are going to do this by doing some examples that seem unrelated. We are going to find the instantaneous velocity of a moving object, and then we are going to find the slope of a line tangent to a curve. So our first example is the following. We have a rock that is launched vertically upward from the ground with a speed of 120 feet per second. The position, or height, of the rock P of t, measured as feet off the ground at time in seconds t, is given by this equation. P of t is equal to negative 16t squared plus 120t. And our first step is we want to find the average velocity of the rock between 1 and 4 seconds. So let's think about this. Most of us have taken some sort of physics class, but even if you haven't, most of us know that the velocity of any object is equal to distance divided by time. Another way to think about this, since we're measuring distance and height, since our rock is being launched vertically upwards, this distance is the change in y. Change in y, this triangle means change, over change in x, because x is our independent variable. Here it is representing time. But another way to think about delta y over delta x, change in y over change in x, this also represents the slope of a line. And we all know how to find the slope of a line. So the slope of a line, again, is change in y over change in x. So I can rewrite this. Our change in y is our function evaluated at 4 and 1, the difference between those two things. So p of 4, our function evaluated at 4, minus our function evaluated at 1. That's our change in y, over our change in x, which is 4 minus 1. Well, if I were to plug in 4 into this equation right here, I would get 224. So this is 224. If I were to plug in 1 into this equation, I would get 104. All of this over 3. 224 minus 104 is 120 over 3. And this is 40. Our units here, well, it's being measured in feet per second. So this is 40 feet per second. This means that the average velocity between t equals 1 and t equals 4 of this rock is 40 feet per second. All right, we have another example, part B, but before I do it with you, I would like for you to pause this video and try to do this one by yourself. We're going to be doing this all term because I like for you to learn with me as I'm showing you how to do the examples. So please pause the video and try this one by yourself. All right, hopefully you have taken the time to do part B on your own. So now let's do it together. So I know that the average velocity, just like we did in part A, is delta y over delta x. In this case, I want to find the average velocity between t equals 1 and t equals 2. So this will be p of 2 minus p of 1 over 2 minus 1. If I plug in 2 into my p of t function, I get 176. If I plug in 1 into my p of t function, I get 104. All of this over 1. So this is 72 feet per second. So the average velocity between t equals 1 and t equals 2 seconds is 72 feet per second. Now I want to represent these two parts on a graph. So how can we represent these things on a graph? Well, if I look at my function, we have p of t is equal to negative 16t squared plus 120. So the negative sign in front of my function here, I'm supposed to highlight it, but anyway, the negative sign means that my parabola is opening downwards. So I know that the graph of this function looks, it's not very straight, looks something like this. It's an upside down parabola. So this is our graph p of t. And I have some times here, right? I wanted to find the average velocity between t equals 1 and t equals 4, as well as t equals 1 and t equals 2. So I found that the height at t equals 1, so this was p of 1, was equal to 104. At 1 second, our rock is 104 feet above the ground if I plug in 1 into my p of t function. I also found that p of 2 was equal to 176 if I plug in 2 into my original function. And if I look at this point right here, p of 4 was equal to 224. So we found the average velocity first between 1 and 4. But as we saw, the average velocity is the same thing as the slope of the line. So this average velocity can also be represented as the slope of the line between t equals 1 and t equals 4. So if I were to draw this on my graph, I could draw the average slope between 1 and 4. I could connect this point right here with this point right here. And this right here represents the average velocity or the slope. So that's between 1 and 4. We found that this was 40 feet per second. If I look between 1 and 2, which was part B, I can draw a line between 1 and 2 here. It's pretty close to the curve itself. And I found this to have a slope of 72. So these two lines, when I connect 1 and p of 1 with 4 and p of 4, this is called a secant line. This is called a secant line. We will be talking about this later on in the term, but it's pretty important for this first section as well. So what does this problem show us? Well, this problem shows us that the average velocity is the slope between the lines joining all of these points. So between the secant lines joining the points 1, oops, and we had 104. That was 1 point. Our other point was 2, 176, and 4, 224. So these are our 3 points. The average velocity can be thought about as the slope between these points. All right, so that was our first example. Again, if you have any questions about this material, please do not hesitate to email me. I would be more than happy to answer any of your questions. And as I mentioned in the course guide, there will also be a discussion board on Canvas for each one of these sections that the TA and I will be monitoring regularly. So if you do have questions, feel free to stick it on the discussion board as well. All right, next we have another example. We want to use the same position formula, P of t, as example 1. We want to estimate the instantaneous velocity of a rock at exactly the time t equals 2. So now we don't have the average velocity here, right? If we look back at problem number 1, we were given 2 times. We wanted to find the average velocity between t equals 1 and t equals 4, and the average velocity between t equals 1 and t equals 2. But in this problem, we want to find the instantaneous velocity at exactly the time t equals 2. We do not have a time range here. So as we did in problem number 1, we know that the average velocity that I'm going to call it v sub average. We know that the average velocity is equal to p of t2 minus p of t1 over t2 minus t1, where these t2 and t1s are just times, right? Here, I only have one time though. I only have t equals 2. So I'm going to plug in t equals 2. I could plug t equals 2 in for t2 or t1. I'm going to do it for t1. So here, I'm going to say p of t2 minus p of 2 over t2 minus 2. So I want this t2 to be very close to t equals 2, right? I have to estimate, so it's not going to be exact, but I want this t2 to be very close to t equals 2 in order to get a really good estimate. So I can do that. I'm going to pick 2.01. So I'm going to call t2 2.01. That gives us a really good estimate. So basically, instead of having an average velocity here in explicit terms, as the problem was asking, I'm basically making an average velocity between a really small time interval, 2.01 and 2. So I can rewrite this. This is p, I called t2 2.01, so this is p of 2.01 minus p of 2 over 2.01 minus 2. Again, this is delta y over delta x. And if I were to plug this into my calculator, and I did the math, I plugged 2.01 and 2 into this original equation right here. I can do the math and I get 55.84 feet per second. But this is not the exact velocity at t equals 2. We had to estimate the velocity at time equals 2 using a number that was really, really, really close to t equals 2. We used 2.01, but it would have been better if we had used 2.001 or 2.000001, right? Because it's getting closer and closer to t equals 2. So we are going to write this in terms of what we call a limit. And this is a very important concept in this class. So I'm going to write it like this. I'm going to write the instantaneous velocity, v sub inst, the instantaneous velocity is equal to the limit as t approaches 2. This means that t is getting very close to 2 of the average velocity. So the instantaneous velocity is basically the average velocity as this t gets really close to 2. In this example, we called it t sub 2, as it gets very close to the actual number that we are trying to evaluate at. So another way that we can think about this is the limit as t goes to 2. T gets very close to 2. And I know the formula for my average velocity, right? It's this guy right here. So this is the limit of p of t minus p of 2 over t minus 2. So this is the instantaneous velocity is the average velocity at a point very close to 2, is what this is saying. Maybe I'll write that here below. The instantaneous velocity is the average velocity at a point very close to t equals 2. So this leads to what we call the slope of a tangent line. If you remember in this example up here, this green and this blue line were what we called secant lines. So this also leads to something else called a tangent line. So here is what a tangent line means. So if I were to look at these secant lines, and if I were to make them in intervals that were very close to t equals 2, then the secant lines would approach what we call a tangent line. And I'll draw this in a minute. So the secant lines approach a unique line called the tangent line. A tangent line touches another graph at exactly one point. Another graph at exactly one point. And has the same slope as the graph at that point. the slopes of the secant lines approach the slope of the tangent line. We're going to call the slope of the secant lines m, that's like the mx plus b, m sub secant. So the slope of these approach the slope of the tangent line. Slope of the tangent line. And I'm going to call the slope of the tangent line m sub tan. Okay, so what does this all look like? Let's draw some pictures here below. Let's first draw a picture of what a tangent line means. So in our examples, we've been using the point 2. In example 2, we wanted to find the instantaneous velocity at exactly the time t equals 2. So if I were to draw a picture of this, my graph looks something like this. And I'm going to call this the point t equals 2. So a tangent line has the same slope of the graph at this exact point. And it touches our graph at only that point to p of 2. So our tangent line looks something like this. This is the tangent line. And if you can imagine, these secant lines that we talked about up here, as these intervals get smaller and smaller and smaller around the point t equals 2, they approach this tangent line here. So what this picture is showing us is that the slope of the tangent line at the point 176 is the limit of the slopes of the secant lines. As t goes to 2. If I wanted to find the secant line instead, I could do that. I could draw another picture. So the secant line, remember, is the line that connects 2 points on a graph. So say I had t equals 2 and t equals 1. If I were to connect these 2 points with a line, like that, then this is the average velocity, or the secant line. So the average velocity between t equals 1 and t equals 2 this is called the secant line. So as we shrink the distance from t equals 2, so if I, instead of going from 1 to 2, I went to 1.5 to 2 or 1.9 to 2, then the slope of the secant line approaches the slope of the tangent line. So let's write this down. As we shrink the distance from t equals 2. So if we went from 1.5 or 1.9 or 1.99, if we found the secant lines from those points instead, the slope of the secant lines of those points approach the slope of the tangent line that we found above. So this is how tangent lines and secant lines are related to each other. The secant line, we can also think about this in terms of average velocity between 2 points. And as we shrink the distance between those 2 points, those secant lines, the slope of the secant lines, approach something that we call the tangent line. Another way to think about the tangent line is the instantaneous velocity at a certain point. So that is the end of the first lesson. Again, I'm going to create a discussion board on Canvas for this section. Please let me know if you have any questions about this. And I hope that you enjoyed our first lesson. I know that I certainly did. And I will see you next time. Have a wonderful day.